Hello everyone. This is slide set number 7. It is about the flexural design of pre-stressed concrete beams. When it comes to pre-stressed beams, we have done the stress check, mainly at two cases. The first one was right at the pre-stress force transfer. This when you apply the pre-stress, it's going to be right at the initial pre-stress force. This is where the stress coming from the strains is going to be high, and most likely you don't have the service load, which means most likely you don't have the additional dead load, and also you don't have the life load. The last item here that we need to work on is going to be the limited state at failure. Some people would prefer to call it limited state at the capacity point. It's not really at failure. Failure here of the concrete is considered when the concrete strain reaches 0.003. If you like, you can call it the capacity point, because we understand that concrete is going to be surviving after this strain. This strain at 0.03 is just a point or a stress strain value that the code would like you to consider for the concrete and not to allow the concrete to go beyond this amount of strain. So we have first, right at the pre-stress force transfer, we're going to have the initial pre-stress force, because it's going to be P sub I. Most likely we're going to have the full self-weight of the beam. This is what we call here the dead load. In some cases, dead load is not there because the entire beam or entire double T is going to be sitting on the floor. Second stage or second limited state is going to be right at the service load. Now, all the pre-stress losses would take place, and in this case, you're going to have P effective is going to be the effective pre-stress force, and with that, you're going to have all the dead load. The entire dead load means that you're going to have the superimposed dead load, which is additional dead load, and also you're going to have the life load, and certainly you're going to have the dead load with it, which is the self weight of the beam. The third here stage that you need to do is going to be the third limited state, is going to be right at the capacity point, which means the beam here is going to be loaded with the factor load. This is why we call it here overload. Overload here means that you're going to be loading it to a load value which is beyond what it's going to be exposed to. We understand here load factor is going to be at least 1.2 dead load plus 1.6 live, or it's going to be 1.4 times dead load. Meaning that I know that the ultimate load is going to be roughly maybe 40% higher than the service load. That's why we call it here overloaded. In this figure, figure 4.2, A, detail A, it shows a pre-stress force location. So we understand here the amount of pre-stress or the pre-stress force is going to be at the lower bottom of this section. Once you apply the pre-stress force, you're going to have lots of compression at the bottom, and you may end up with some tension on the top. This is a stress distribution shown in B. Now in C, you start here to apply the dead load, which means the self-weight of the beam. Now once you apply here the dead load is going to be causing tension at the bottom and compression on the top. So the amount of compression that you have here at the bottom is going to start to reduce. The reason is because you're adding here some tension to it. The tension on the top that you have from the pre-stress force is going to get reduced because now you are adding compression to it coming from the dead load effect. So at the stress distribution of C, now we have the pre-stress force, and also you have the dead load. Now after this at D, you're going to have the total dead load, and you're going to have the effective pre-stress force, which means now pre-stress loss is going to be taking its place. Now you have the dead load, and then you're going to have the additional dead load with it. In figure E, now we are gonna having here the life load. It's gonna be added. Once you add the life load, what's gonna happen? You are gonna have more compression on the top. Now you're gonna start to see here some tension on the bottom. If you allow in your design tension to happen and cracks to happen on the bottom. Now in section F, this gives you the capacity point. I prefer to call the capacity point rather than the failure point. As you see here, the stress distribution is going to be taking the same shape as the stress-strain relationship of the concrete. C lowercase is going to be depth of neutral axis. Also, we have studied this load deformation curve for the pre-stressed beam. We understand at the beginning, we're going to be applying here the pre-stress force, and you see here deformation or camber is going to happen to your beam. Deformation is general term here that used for movement of the beam, whether it goes up or goes down. If it goes up, we call it camber. If it goes down, we call it deflection. As long as you're giving the left side of the vertical axis, which is the load, we're going to call this camber. Once you go here to the right side, we're going to call this deflection. The capacity point is going to be all the way in the top, the one in the red box. If you go to the point right before it, this point is called service load limit. Service load limit includes all the service load, which means dead load, additional dead load, and life load. And to take it from the service load all the way to the ultimate load, you have roughly about 40% of the total service load. In this slide here, I have the load combinations for the ultimate load design. This can be the one such as 1.4 dead versus 1.2 dead plus 1.6 life. This can be based here on the California Building Code, which is based on the IBC International Building Code. When you do any design, you need to have a capacity more than the demand. Demand is going to be taking the term sub U, like P sub U is going to be axial load demand, M sub U is going to be flexural demand or moment demand, V sub U is going to be shear demand, and so forth. Once you see here phi Pn, phi Mn, and phi Vn is going to be the axial, flexural or moment, and shear capacity. Phi is going to be the stress reduction factor, and sub n means nominal. So what is again P sub U? This is going to be ultimate axial load. How do you do here ultimate axial load? This is going to happen when you have columns or certain structural members subjected to axial load. Ultimate flexural load is going to be the moment, which is rotation forces or rotational load. And this is going to be the standard moment that you use when it comes to beams. Same thing when it comes to shear. This slide here includes the analysis of conventional concrete section design. This for non-pre-stressed beams. This is the conventional concrete design that we're used to. We have certain assumptions. First, look at the first detail on the left-hand side. Depth to the reinforcing bars from the compression, top compression is going to be called D. Total depth of the beam is called H. The width is called B. The strain distribution here is assumed to be linearly distributed throughout the depth of the beam. Look here at the first assumption. It says here plan sections remain plan after bending. This assumption confirms the fact that we're trying to simplify the strain distribution within the beam, and we go to be linearly distributed like the way that you're looking here at. The capacity point, as it says here in assumption number 3, is going to be equal to concrete strain of 0.003. We understand that concrete, generally speaking, would be able to approach easily 0.004 strain without failure. But according to the code, this is going to be the capacity point. To simplify the stress distribution, in the compression on the concrete, we're going to be assuming here a block. This block is going to have a stress value of 0.85 F prime sub C. The depth of it is going to be called A, which is equals to beta 1, which is a factor based on the concrete strength, multiplied by C, which is a neutral axis depth. The tensor reinforcing, we assume that's going to be yielding. Therefore, the tension in the steel is going to be equal to A sub S multiplied by F sub Y. Also, this is going to be equal to the compression of the concrete. Compression of the concrete is 0.85 multiplied by F prime C multiplied by B times A, which is a compression block depth. When you start the problem here, most likely the moment is going to be given to you. So you have the moment demand. The beam section, which means length by depth, depth by width if you like, you can either estimate it or it's going to be given to you. Amount of reinforcing, you can start by putting the first estimate, which means that you are going to be assuming here the amount of AS that you have for the beam. Tension in the reinforcing bars is going to be equal to AS times Fy. I understand the tension is going to be the same as the compression, so let them be equal to each other. T is going to be equal to C. Based on this, I can come up with an equation to determine the compression block depth A. In this equation here, when you have higher amount of reinforcing, depth A is going to be going up. When you have bigger width of the beam, compression block depth is going to be going down. At the end, nominal moment of this section is going to be equal to either tension or compression multiplied by the distance from this force tension to the force compression C. Some references would call this distance as the depth YC-T. YC-T means the distance from the compression to the tension. Other references may call it Z. Therefore, Mn is going to be equal to As times Fy, which means the tension force, which is the same as the compression force. You multiply this by D minus A over 2. Certainly, after you're going to be using the phi factor, you take here Mn multiplied by the phi factor. Now, when you have a beam with compression reinforcing, what's going to happen? Compression reinforcing means that you're going to have some top reinforcing bars, because top of the beam is going to be exposed to compression. In section A, I have all the symbols used for geometrical properties. I have the depth D. Depth D is going to be the distance from the top compression all the way to the tensor reinforcing bars. D prime is the distance from the top compression to the compression rebars AS prime. This is why it's called D prime. The strain in the steel at the bottom is going to be called epsilon S. Now I'm looking at figure B. Concrete compression is assumed to be, and the strain is assumed to be 0.003. Let's give it the capacity point. The strain in the compression steel is going to be named epsilon prime S. C lowercase is going to be depth of the neutral axis. That was the strain distribution. Now when it comes to forces, I'm going to split it into two graphs. It's going to be C and D. The first one, which is C, I'm going to be taking here the compression of the concrete. I'm going to be calling it C1. Stress value is going to be 0.85 A prime C. The depth of it is going to be equals to A. Now let me here move for a second to graph D. I'm going to have here the compression on the top is going to be called C sub 2. And this compression is going to be the compression and the top reinforcing, which means the compression steel. It's going to be equal to AS prime multiplied by FS prime. I understand the AS prime is going to be total cross-section area of the compression steel. Fs prime is going to be the stress in the top steel. I don't know if the compression steel is going to be new or not. That's why I have used it as Fs prime. So now what happened, I split the compression forces into two separate graphs. Now how about the tension force? Tension force is going to be equal to As times F sub y. Because most likely we designed the tension reinforcing at the bottom to yield. Now since I split the two compression forces, and my understanding is C1 plus C2 is going to be equal to the tension force, now also I can split the tension force into two tensile forces. I'm going to have here T1 and T2. And the total AS, I'm going to split it here into two cross-sectional areas. I'm going to have here AS1 and AS2. You simply can say AS is going to be equal to AS1 plus AS2. I understand that. Why are we doing this? The reason because we'd like to simplify the problem. Now T1 is going to be equal to C1 and T2 is going to be equal to C sub 2. The distance from the compression to the tension is going to be called Z. So in the case of C1 and T1, we may call it Z1. In the case of C2 and T2, I'm going to call it here Z2. Distance here, Z1, is going to be equal to depth of the tensor reinforcing subtracting A over 2. Z sub 2 or Z2 is going to be equal to the depth D subtracting the depth of the compression reinforcing, which is D prime. So it's going to be equal to D minus D prime. Now if you like here to determine the nominal moment is going to be equal to T1 multiplied by Z1 plus T2 multiplied by Z2. Now to determine B1, you can use this slide. According to the ACI code, beta 1, it is equal to 0.85 when the concrete strength at 28 days is 4000 psi or less. Once the concrete strength is equal to 8000 psi or more, this beta 1 is going to be equal to 0.65. That's why in the graph, look here on the x-axis, you have the concrete strength. On the y-axis, you have the beta 1 value. For 4000 and below, your beta 1 equals 0.85. For 8000 and higher, your beta 1 is equal to 0.65. It is allowed to interpolate between the two values, which means for each additional 1000 psi increase, you're going to have a drop in beta 1 of 0.05. This slide here is going to be for the phi factor, the stress reduction factor. On the x-axis, you may have either epsilon sub t, which is the strain in the tensile steel, or you can have C, neutral active depths, divided by dt. D sub t here is going to be the depth to the tensor reinforcing bars, which is the standard D that we use in our analysis. You need to note that epsilon t is increasing in the east direction, which means for this arrow running east. You see here the first point is going to be at 0.002. Second point is going to be 0.005, which means the increased direction is going to be for this arrow running east. For C over D ratio, which means the depth of the neutral axis to the depth of the tensor reinforcing bars, it increases with this arrow that goes west. As we see here, the first point here on the right side is going to be 0.375 for this ratio, and on the left side is going to be equal to 0.6. So this is going to be direction of increase. For our pre-stressed beams, we're not going to have any spiral columns or spiral beams. We don't have this. We're going to have other. So I'm going to be using here the solid line. Phi factor here is shown on the y-axis. So I have either tension controlled, as you see here on the right hand side, or transition. I'm going to have here compression controlled section. Tension controlled means that the strain in the steel is equal to 0.005 or more. Compression when the strain in the steel is equal to 0.002 or less. If the strain in the steel is in between, you can use this interpolation equation, which is written right there in the middle of the graph. It says phi equals 0.65 plus, and then you just can continue here. Now when I have here pre-stressed section, I'm gonna have here combination of regular reinforcing bars and pre-stressed tendons, if you like. In this slide, we are showing only the amount of pre-stressed tendons. As you see here, previously, when I have here conventional reinforcing concrete design, we used to use F sub y. In our case here for pre-stressed cables or tendons, we're gonna have here FPI, FPE, and eventually for the capacity point is gonna be FPS. Now FPS definition of it is gonna be the steel nominal failure stress. Let's not call it here failure. If you like, I would call it the capacity stress, which means, or the nominal stress, which means the stress at which we're going to be using to determine the capacity of the section when it comes to flexion. The actual stress distribution is going to be shown right here in the middle on the top of this slide. The width of the beam is called B, depth of neutral axis is going to be C lowercase, compression force is going to be C, the tension is going to be APS, which means cross-section area of the pre-stress strength or steel multiplied by FPS. This can be the amount of tension force. This here can be reduced. I'm talking here about the complexity of the stress distribution. It can be reduced for the neutral axis depth C, we can make it A, and the stress is going to be 0.85 A prime C. And then you can continue. Now instead of having the depth is going to be called D, I'm going to call it here D sub P, depth to the pre-stress. Instead of AS is going to be A sub PS, which means for the pre-stress strength or steel. The rest of the analysis is going to be very similar to what we used to do for conventional concrete design. So again, differences between pre-stressed beam and non-pre-stressed beam is going to be the definition of DP, depth to the pre-stress, and APS. And the remainder of the analysis is going to be very similar to that of the conventional pre-stressed, conventional reinforced concrete design. Excuse me for that. Now, generally speaking, when you have pre-stressed strains and non-pre-stressed rebars, total tension force at the bottom is going to be equal to ASFY, it's going to be for the non-tension steel, and plus APS, which means the strains, times FPS, nominal stress for the strains. Compression force is going to be 0.85 F prime C BA. It's going to be very similar to the conventional concrete design. Now we set the tension is going to be equal to compression. With that, we should be able to solve for A, which is compression block depth. A is going to be equals to ASFY plus APS times FPS. You divide this by 0.85 F prime C times B. Now if you like to figure out here the nominal flexure strength, you're going to be taking Mn is going to be equal to T coming from the pre-stress times what? Times Z1 plus T coming from the conventional rebars, non-tension rebars, non-pre-stress rebars times Z that goes with it, which means D minus A over 2. Now phi Mn, which is the flexure strength or capacity of the section when it comes to flexure, is going to be equal to phi factor multiplied by M sub n. Question is, how do you figure out this FPS, nominal steel stress, for the pre-stressed strain? The ACI here gives you an equation. It's kind of simplifying it. It says here FPS is going to be equal to F sub PU. FPU, as we said, is going to be equal to the 270 case sign. And then multiply by a big factor. This big factor, I'm sure it has to be less than 1. Because you cannot go here to a stress and use it for the capacity of the beam to be higher than FPU. And it cannot be equals to FPU. It needs to be less than FPU. Therefore, this big factor or this big term needs to be less than 1. It says here 1 minus, so 1 subtracting something. And this something here, this term inside, this subtractive term, is going to be all negative because it says minus and then the term itself is going to be positive. So I know now for sure that FPS is going to be lower than FPU. It shows here some terms like beta 1, like gamma sub p. This is something that I need to work on. We need to understand where it's coming from. Rho sub p, F sub pu, yeah I know it, F prime c, depth d to the conventional rebars, depth p to the pre-stress, F sub y for the stress, yield strength of the steel, F prime c again, rho and rho prime. The symbol rho here is usually used for the steel ratio. So rho is going to be the tensile steel ratio, is going to be the ratio of AS divided by B divided by D, and rho prime is going to be AS prime divided by B times D. Now the question is, what is this gamma sub P? In the code, I have these two tables. For the ASTM 0416, for stress relieved strengths, which most likely this is going to be the one we use, yield strength to the ultimate strength of the pre-stress strengths is going to be nearly 0.85 and higher. For a case like this, FPY divided by FPU, and it is 0.85 and higher, gamma sub P that you're going to be using in your equation is going to be equals to 0.4. So this gamma sub P is equal to 0.4 for all strains that you're going to be using in this course. Now I understand where it's coming from. It is a code value that we're going to be using out of some tables, and here are the tables. Now what happened here? When D prime is really big, which means when the top reinforcing is coming a little bit down when it comes to top or bottom, code just says ignore it in this equation. In the equation of FPS, do not consider here D prime in this case. Reasons because it's not really contributing much to the compression, so you can just ignore it. And if compression reinforcement is used, this term here that you're looking at, which is rho p FPU divided by F prime c, the entire term here cannot be less than 0.17. And here's the reason. Once you start to add here rho prime, what's going to happen? Rho prime is going to be reducing this term, the entire term. And they don't want you to reduce this term by much. So they put here a limit. They say that this term shall not be taken less than 0.17. Otherwise, you can just add lots of reinforcing bars into compression, and with that you increase the amount of FPS. They'd like to put a limit. In your analysis to design the pre-stressed beam, one important point that you need to look at is give you the cracking moment of this beam. Where do you think the cracking is going to happen? Generally speaking, cracking is going to happen on the bottom of the beam, and this is going to be the part of the beam exposed to tension. Cracking is going to happen once the bottom stress is going to be reaching or going beyond a stress value of 7.5 is equal to F prime C. Please remember that this code here, the ACI, is a PSI code, which means F prime C needs to be in PSI. We have this equation that we used to use and we still use. It shows here the stress at the bottom is going to be equal to P effective negative P effective divided by AC, and also includes total moment effect divided by S sub B. I'm not sure if I'm going to have here the total moment or not. Is this moment is going to be what? This moment is going to be due to dead load, due to dead load and additional dead load, due to dead load, additional dead load, and life load. Well, I'm not sure of this because we don't know exactly how much is the moment causing cracking of the beam. So I'm going to say this moment here, I'm going to be calling it the cracking moment. And the stress in this equation is going to be equal to F sub R, which is a 7.5 square root of F prime C. So this moment is going to be causing the stress to be equals to 7.5 square root of F prime C. I'm going to be calling the cracking moment. So instead of MT, I'm going to be replacing it with M cracking. And instead of F sub B, I'm going to replace it with F sub R, which is a 7.5 square root of F prime C. We can rewrite the equation. At the end, at the bottom, I have here the cracking moment equals the effective pre-stress force times E plus R squared, radius of gyration squared, divided by C sub B, plus F sub R multiplied by S sub B, section modulus, and the stress 7.5 square root of A prime C. We have one example here, example 7.1. I have a given I-beam for a bridge. Concrete strength is given as 5,000 psi. I have here all the properties of this concrete beam, such as the depth, the width of the top flange, bottom, it looks like kind of an I section. I have the moment of inertia given in the table. I have radius of gyration squared. I have total cross-section area of the concrete. I have C to the top, neutral axis, and actually from the CG all the way to the top. I have S top, I have C to the bottom, distance from the CG of the beam all the way to the bottom of the beam. I have section modulus of the bottom. I have WD, which means the dead load is going to be 393 pound per linear foot. The span is given as 65 feet. Dead load as given previously in the previous slide is going to be 393 pound per linear foot. Additional dead load or superimposed dead load, WSDL, is going to be 100 PLF. The life load is kind of a little bit higher. It's going to be 1.1 KLF, K per linear foot. This beam here includes 13.5 an inch, A4 16 strengths. The one with F sub U of 270 KSI. I have also non-tension steel. It's going to be conventional rebars. It's going to be 4 number 6s. And it tells me here to use FPE of 155 KSI. Effective pre-stress is going to be 155 KSI. I have 4 items here that I need to do. Item number 1, it says determine the cracking moment. Item number 2, for the given loads. What loads? I'm going to say, yeah, loads right above. Dead load, superimposed dead load, and life load. Determine the load stage at which the beam will crack. So I need to know exactly where the beam is going to crack. Is it once you apply the dead load? Is it once you start to apply the superimposed dead load to the dead load? Or is it once you apply the life load? Or it will never crack. I need to know exactly the amount of cracks that's going to happen with this beam. Then it says here, determine the overload moment beyond the cracking point. Now I need to know if the cracking point is going to happen below I apply all the loads. So let's say here for a second that the cracking is going to happen once I start here to apply the superimposed dead load. Right after I apply the superimposed dead load, which means cracking is going to happen, let's say just for sake of discussion, at this slide only, is going to happen at 493. How do I come up with this? I add here the 100 to the 393. Let's say here 493 P left. It means I'm gonna stay here have long way for the live load above the cracking. Let's say another scenario. I added dead load, I add superimposed dead load, I add maybe 1000 PLF of the live load and no cracking is happening. Once you start here to add one more PLF above the 1493 PLF, I start here to see some cracking. Therefore, I'm going to say the overload moment beyond the cracking is going to be very limited. Why? Because I applied most of the loads that I have for the service, including dead load, superimposed dead load, and most of the live load, and then I'm going to start here to see some cracking. So the amount of overload beyond the cracking point is going to be very small. This here gives me an indication of how much cracking do I expect, or how much cracking beyond that point is expected. Last item that you need to determine is going to be the safety factor against cracking. Whether we're going to have some cracking or no cracking at all, or where do we stand when it comes to cracking. So in this slide, we're repeating again the span, self-weight, which is a dead load, additional dead load or superimposed dead load, and the live load. The moment only due to dead load is calculated out as W squared divided by 8. Same thing for the additional dead load and same thing for the live load. Now I have the three moments for each different load separately. The beam includes 13.5 inch ASTM A416 strands, 270K. The FPE, the effective stress, we are not going to be using 150 KSI. Instead, we will be using here 155 KSI in this problem only. Total cross-sectional area of all the strands is going to be equal to 13 multiplied by the cross-sectional area of 1/2 inch strand, which is 0.156. You have a total here of 1.99 square inches. Effective pre-stress force is going to be equal to APS, total cross-sectional area of the strands multiplied by the effective pre-stress. This is going to be a total of 308.45 kips. To determine the cracking moment, I'm going to be using the equation that we had a few slides ago. This equation here relates the cracking moment with the effective pre-stress force, eccentricity of the pre-stress force, beam geometrical properties, and this is included here in R squared divided by C sub B. The cracking stress according to the ACI, the 7.5 square root of F prime C, and the section modulus, which is also the property of the pre-stressed concrete beam section. The stress for the concrete of 5000 psi. We have here a cracking stress at 530 psi, meaning that once the bottom stress in the beam is going to be reaching 530 psi, the beam is going to start to crack. Look here at the bottom equation, the bottom line, the cracking moment. It is going to be 781.24 kfoot. So roughly at 781 kfoot, this beam is going to start to crack. Now, the moment due to dead load, which is a self-weight only, is roughly about 208 kfoot. For superimposed dead load, let's say about 53 kfoot. Due to live load, maybe 581 kfoot. Now, I understand that the cracking moment is 781 kfoot, which means with having the self-weight only applied to the concrete beam, I'm not going to see any cracking, simply because moment due to dead load is 208 and the cracking is 781, so we're not close to the cracking point yet. Now you start here to add the superimposed dead load. Now we are going to be at 260.36 kfoot. As you see here, M dead load plus M superimposed dead load. Now we are at 260. We're not close yet to the cracking moment. Now once here you start to apply the life load, once you have it in there, now total moment, total service load moment, dead load plus superimposed dead load plus life load is gonna be 841. Now the beam is gonna crack. Look here at the total load. Total load is 841, the applied load. The cracking moment is gonna be 781. Now we'd like to figure out here how much is this overload moment, which means the difference between the total moment that you have due to the service loads and between the cracking moment. Difference between the two, as you see here in the overload moment, is going to be about 60 kfoot, which means while you're applying the life load, before you complete 100% of the life load, the beam starts to crack. Now we have here safety factor against the cracking. Safety factor is going to be equal to the cracking moment divided by the total moment. It's going to be 0.93. This means once you are at 93% of the total service load, your beam is going to crack. And this is the indication that we're looking for as a safety factor against cracking. Let's assume here for a second that the cracking moment is higher than the total service load. Now it's going to happen. Your safety factor against cracking is going to be more than 1, which means your beam is not going to crack according to the given service loads. I have another example. This is example 7.2. Exactly same beam, same previous beam, same geometrical properties, same additional dead load. And the additional dead load is here is going to be the 3-inch concrete slab topping. In this problem here, it says ignore the trends of the topping slab, which means the topping slab is going to be just ignored. It's true that we have it there. It helps the compression flange on the top, but it's going to be ignored in our analysis. I have the same information when it comes to loading. Same dead load, same superimposed dead load, same life load. Same number of strands is going to be 13.5 inch ASTM A416 strands. Same FPE, which means the same prestress that we're going to be using. The EPS, which is the modulus plasticity for the strands, is given as 28,000 KSI. You need to note that usually it is 29,000 KSI for other reinforcing, but for this strength is going to be taken as 28,000 KSI. Now the centroid of the strength is going to be at 15 inches below the CG of the beam, which means right at the midspan, all the cable to the strength is going to be at 15 inches from the CG of the beam. I have here some non-prestressed steel, which is a conventional rebars, is going to be placed with 1.5 inch clear cover from the bottom. There is no compression steel that I can consider here in my analysis. The question here is to complete my design, determine the factored moment, which means the design moment, the demand, M sub U, and also determine the flexural capacity, which means phi man. We'd like to see here the demand versus capacity when it comes to the beam. With this example here, we're going to be done with one good example for a pre-stressed beam that we start by doing the cracking moment. And usually once you do the cracking moment, it's going to be a service calculation, which means all the load is going to be at the service. But once it comes here to the capacity, the flexural strength phi man, I need to have factored. So, as we said, the span is going to be 65 feet. Now I have dead load, superimposed dead load, and life load. Now also I have the moment due to dead load, moment due to superimposed dead load, and moment due to life load, and all of that we have determined this previously in the previous example. Now the ultimate in this case is going to be equals to 1.2 dead load plus 1.6 life load. Now dead load and superimposed dead load can be added together, multiplied by 1.2, and the live load is given multiplied by 1.6. If you are doing a homework problem or exam problem, you certainly need also to try 1.4 times M dead load, but it's gonna be much lower than 1241.94 kPa anyways. Now, looking at the analysis for concrete section, when you have this pre-stress, the nominal pre-stress that we're going to be using, FPS, we have two ways of doing it. We have one way is kind of detailed way, and the other method is going to be the simplified as given by the ACI. This is going to be that simple equation that we can just use. In here, we're going to have two forces. We have the tension force due to the pre-stress, and we have the compression force in the concrete. In our example, we're going to have here two tension forces. Reasons because I have here the pre-stress and also I have the reinforcing bars. And both of them, they're going to be at the bottom of the section, right in the middle of the concrete beam. So this is going to be the point that we need to work on. The point is at the capacity point. I don't like to call it failure because this is actually the capacity point. APS is going to be equal to 13.5 inch strands, ASTM A416. Each one of the strands is going to be 0.153 square inches. I have 13 of them. I have 1.99 square inches. Ultimate strength for these cables, these strands, is 270 KSI, while the effective pre-stress equals 155 KSI. Effective force is going to be equal to the total cross-section area of the strands multiplied by FPE. You have here 308.45 kips. Now let's look here at the strain and the strength. If I know that the stress in the strength is going to be 155, I know here the modulus of elasticity, the 28,000 KSI, you should be able to figure out the strain. This is because the modulus of elasticity, it is equal to the stress divided by the strain. Now I have the stress, it's going to be 155 KSI. I have E sub PS, which is the modulus of elasticity. I should be able to figure out the amount of strain in the strains. This is determined here to be 0.0055. The second component for the strain and the strains is going to be coming from the decompression by the external applied force. External applied force, which means the load is coming to the beam. The modulus of elasticity for the concrete can be determined using this equation here. E sub C equals to 57. If you like to call it 57,000 square root of F prime C, and the whole answer is going to be in PSI. Since I'd like to have the answer in KSI, I'm going to just be using here the 57 without the 1000, because as if I'm dividing the whole equation here by 1000. You still need to use F prime C as in PSI to be 5000. With that, I have the modulus of elasticity for the concrete roughly 4000 KSI. I understand the eccentricity is going to be equal to 15 inches. That was given the problem. Due to this decompression, now let's look here at the effective force that we have. Effective force is going to be 308.45 concrete cross-sectional area. I have E sub C, and then you say here 1 plus E squared divided by R squared. This is actually the equation that we can use here to determine the amount of strain in the strength, and this because of the applied loads on the top of the concrete. This is determined here to be 0.0004. This here needs to be added the previous calculated strain due to the applied pre-stress force. So this slide here, it shows geometrical properties. So what we're trying to do is to find out the depth to the pre-stress strengths and also the depth to the conventional rebars, the 4 number 6s. First, the depth to the non-pre-stressed rebars, conventional rebars. We can take it as 40 inches total depth of the concrete beam. You subtract here 1.5 inch clear, and then you have the tie. The tie, I'm gonna say, I understand it says here is give you number 3, but I'm gonna give it like half an inch. And then also you have for the rebars itself is 3/4 of an inch. So I'm gonna say for 3/4 inch, you divide this by 2 to get to the radius of the rebar. You're gonna have here about 37.6 inches. Eccentricity is given as 15 inches. Eccentricity means location of the pre-stress strength from the CG, the centroid of the center of gravity of the concrete section. dP is going to be equal to this 15 inch plus the distance from the centroid to the top of the beam. Just imagine here centroid is going to be, let's say, in the mid-height of, close to the mid-height of the concrete beam depth. And to be exact, it's going to be located at 21.16 inch from the top. And the location of the pre-stress strength from the centroid of this section is at 15 inches. So for that, the distance from the top of the beam to the center of the pre-strength is going to be equal to 15 inch plus 21.16 gives you here 36.16 inches. Total cross-section area of non-pre-stressed rebars. They are 4 number 6s, so 4 times 0.44 is going to be 1.76 square inches. Now beta 1, we can determine this based on this chart. For 5,000, I can say first for 4,000 I have 0.85. For additional 1,000 with psi, I'm going to have a drop of 0.05 in the beta 1 value. Therefore, beta 1 be equal to 0.8. This third component for the strain of the steel is going to be coming from the capacity point. In the capacity point, we should be able to determine the compression block depth A if we have the total tension in the steel, we have the concrete strength, and the width of the concrete beam. To start with the stress, nominal stress in the pre-strength, I need to start from some point. So I'm going to be assuming here that the nominal stress is equal to 205 psi. It's kind of on the low side, and this is going to be a good starting point. You can start with 210 psi if you'd like to. With running this equation and considering the width of the beam to be 18 inches, which is the width of the top bulb in the concrete beam, you end up with here compression block depth of 6.71 inches. Now, the neutral axis depth can be determined if you take this value here of A divided this by beta 1 of 0.8. With that, you have here 8.39 inches. Now, with these two similar triangles, we're doing the strain compatibility equation. And to determine the strain right at the strengths, you can determine here that the epsilon 3 is going to be equal to 0.01 strain. And for that, this strain here is higher than the 0.005, and this is going to be the limit at which we decide whether the phi factor is going to be 0.9 or is going to be in the transition zone according to the ACI. 0.01 is pretty high, so I know here for sure that the phi factor is going to be equal to 0.9. Now I have three components for the strain in the strengths. The first one is coming from the pre-stress. It's going to be 0.0055 as we determined before. The second component is going to be coming from the loading on the concrete beam. Is going to be equal to 0.0004. The third one here is going to be coming from the ultimate point, which means the capacity point. Total strain is going to be roughly 0.0163. Now let's go back here to the stress-strain relationship for 270K pre-stress strengths. If you have the amount of strain on the x-axis, the stress is going to be on the y-axis. You draw a vertical line at the strain of 0.016. Once it hits the curve, the stress strain curve, you go horizontal, and with that you can figure out the amount of stress that you can use as nominal stress. It is determined here to be roughly 229 ksi, which is higher than the 205 and started with. This is good news. My assumption was okay. Going back here again to the phi factor, since the strain is going to be much higher than 0.005 on the x-axis, is going to be in the tension controlled zone, and the phi factor is going to be equal to 0.9. Now to determine here the flexural stress, which means phi mn, is going to be equal to the phi factor 0.9 plus the first tension force coming from the strength is going to be APS 1.99 multiplied by FPS that we just determined. You multiply this by Z1. What is Z1 here? It's going to be dP subtracting A over 2. dP is a value, is going to be the depth of the pre-stress strength, 3616, subtracting 1/2 of A. Plus, other component is going to be coming from the non-tensioned rebars, conventional rebars. This is going to be equal to the 1.76 total cross-section area for 4 number 6s, multiply here by 60 ksi, and then you say here d minus a over 2. Now this depth, the 37.6, is going to be to the centroid of the non-tensioned rebar. Your answer here, of course, is going to be in kip inch, since you have used here kips and inches when it comes to the z value. You divide this by 12, and with that you have 1379 kfoot. Here's the good thing. 1379 is greater than the ultimate moment, which is 1242 roughly, which means here your phi min is greater than m sub u. The last thing that you'd like to do here is to determine here the nominal steel stress for the strength. I'm going to be using here the ACI equation, which is a simplified method. The other one was kind of more details that you need to figure out exactly how much strain you have here in the concrete strength, in the concrete beam strength. FPS is going to be equal to FPU, the 270, multiplied by a reduction factor. This here, how to calculate the reduction factor. As we said here, beta gamma sub P is going to be equal to 0.4. Rho, which is the steel reinforcing ratio, is going to be equal to 1.76 for number 6s divided by total cross-section area of the concrete section, 377. I have it here as 0.0047. For the pre-stress steel ratio, it's going to be 1.99. You have here 13 half-inch strengths. It's going to be 1.99. You divide this by the 377 total cross-section area of the concrete beam. With that, I have 0.0053. I don't have any rho prime because there is no compression steel. So when it comes to the equation, rho prime is going to be taken as 0. Look here at the equation. You start here with 270 and then just complete the equation based on the values that we determined for each one of these variables. If you like to use here KSI in this equation should be fine, because you have usually F sub Y divided by F prime C, FPU divided by F prime C. So it's going to be 1000 divided by 1000, so it can cancel out. With that, FPS based on the ACI equation is equal to 231 KSI, which is not bad. This is actually very close. This is going to be the end of this presentation, and we'll continue.